Hey everyone, welcome to another session of Ceerazzledazzlephysics. In today's session, we've been talking about nuclear fusion, guys. So put down today's title, it's going to be nuclear fusion. Before we get going, guys, make sure you hit the like and subscribe button to keep my channel going and keep my content as free as possible, guys. Okay, so first of all, let's have a quick recap. What is fusion and how is it different to fission, guys? So previously in this topic, we've talked about the concept of fission. Fission is when we had a large nucleus, as you can see, and it splits. So we have a large nucleus and it splits into smaller, lighter nuclei and energy is released. So as you can see, the large nucleus at the top over here, it's going to split and we get energy released, guys. So energy is also released in this whole process. But what exactly is fusion? Well, fusion is a bit different. Key thing is, think about the word fusion, fuse. If you're going to fuse, it's not going to be splitting, it's going to be fusing, bringing things together. So it's going to be almost like the reverse of fission. So fusion will be defined as the following. Fusion, combining lighter nuclei together to make larger, heavier nuclei, plus releasing energy, guys. So there you go. As you can see, I've drawn the fusion reaction taking place. So the lighter nuclei over here, we are going to combine them to make a larger nuclei over here. Plus we get energy released in this process. So energy is released in this process also, guys. So energy is released in this process also. So it's kind of like the opposite of nuclear fission, guys. So in nuclear fission, you have the large nucleus which splits, releasing energy. In fusion, you have the lighter, smaller nuclei which are going to be combined together, fused together to make a larger nucleus, and energy is released in this process. Easy stuff. Okay, so the next question will be the following. Where does the energy come from in fusion? Where does the energy come from in fusion? Where does that energy come from? So as you can see, we've got a before stage and we've got an after stage right now. So we said before they were separate, and then in the after stage you've combined them into one. But where is that extra energy coming from? Well, look at this. Let's put some numbers in here to give us a bit of perspective. Let's say the first one, this one over here, is 1 gram, the other one over here is 1 gram over here, but when they've been combined together, the total mass of this nucleus is 1.5 grams. Okay, so obviously you can see something's a bit different between them. There's a difference in mass before and afterwards. So you should hopefully have the idea that the conservation of mass means that the total mass before should be equal to the total mass afterwards. There you go, guys. So I'll put it down. The total mass before should be equal to the total mass afterwards. So therefore you have 1 gram plus another 1 gram over here. That should be equal to what's on this side over here, but we've got 1.5 grams. So clearly they're not the same because it should be 2 grams over here. It's not equal to 1.5 grams. So there's a problem. Well, that difference in mass, so obviously we can work out the difference in mass before and afterwards. That difference in mass is converted into energy, guys. So that difference in mass is converted into the energy. That's where the energy comes from. Let's put that down. There we go. As you can see on the right hand side, the difference in mass before and after fusion is converted into energy. And as you can see in this, the difference in mass, we'll call that delta M, which is the change in mass. It's going to be, well, obviously we have 2 grams before minus 1.5, so 2 minus 1.5 grams. Therefore, it's equal to 0.5 grams. Well, that 0.5 grams will be converted into energy, and that's where Einstein's equation of the energy is equal to mass times by the speed of light squared comes from, guys. So you can take that mass and times it by the speed of light and it will tell you the energy. That's a bit more advanced, but it's nice to know, guys. Easy stuff. Okay, so now we have the following. Where does fusion occur? Where does fusion occur? Where does it occur, guys, naturally? Well, guys, it occurs in the stars, guys. So it occurs naturally within the stars. There we go, guys. So naturally it occurs in the stars, and in the stars, guys, hopefully you remember that we have hydrogen, which is being constantly fused into helium, guys. So fusion naturally occurs in the stars. The next question is going to be the following. Why should we explore fusion? Why should we explore fusion? What is the benefit of exploring fusion? Okay, so right now on Earth we have loads of water, loads and loads of water. Imagine we could take all that water and we fuse it together to produce heavy nuclei and release energy for our electricity generation. Well, there you go, we could possibly solve our energy crisis. So that's one reason why we can look at it. But also, a second reason would be that the energy released in fusion is going to be greater than the energy released from fission. So it releases a great amount of energy per kilogram of fuel. Okay, and the last question is going to be the following. Why is it difficult to build fusion reactors on Earth? Because obviously if we've got all this fuel here, can't we just fuse it all together? Why is it difficult? Well, think about the actual process. What's going to be really difficult when you take the nucleus of one atom and you try and bring it next to the nucleus of another atom to fuse together? Well, think about what's going to happen. What is the charge of the nucleus? Right, so let's just say we're going to fuse hydrogen. So in hydrogen, you've got a proton in the nucleus, and obviously it's positively charged. And let's say you want to fuse it with another hydrogen nuclei. There we go. And obviously it's another proton. Obviously inside the nucleus there's only one proton in both of them. If you're trying to fuse these both together, surely we can see that they both have the same charge. So obviously they have the same charge. We know that like charges will repel. So there is a repulsion between them. So you've got to overcome this repulsion, guys. And that's going to require lots of high temperature so that they're going to move very fast so they can collide, and you need high amounts of pressure, which we can't really do on Earth. There are some nuclear fusion reactors which they're trying to look into, but right now it's really difficult for us to do. So just a quick recap, the reason why it's difficult to bring these guys together is because they are repelled from one another. That's the first reason, and therefore you need high temperatures and high pressure to get that going, guys. There you go, guys. I've put it down right now. There is an electrostatic repulsion between them because they're both positively charged between the nuclei, and therefore we need very high temperature and very high pressure for that to occur. And that's the reason why it's difficult for us to build fusion reactors on Earth right now. Easy stuff. Okay, so we're done with another session. Let's have a quick recap right from the top. Nuclear fusion, guys, was today's title, and then we talked about the difference between fusion and how it's different from fission. So in fission, the large nuclei is going to split, releasing energy. In fusion, the smaller, lighter nuclei is going to combine into a heavier one, releasing energy, guys. So that's going to be the difference between nuclear fission and fusion. And then we talked about where does the energy come from in nuclear fusion? Well, the difference in mass of everything before and everything afterwards, that difference in mass is converted into energy, guys. Because if you were to look at the total mass of everything before, total mass afterwards, they're not the same. That difference in mass, which is going to be over here, you can see the difference in mass is 0.5. That is then converted into energy using Einstein's equation, E is equal to mc squared. You don't have to know that one, yeah? But it's nice for us to know a bit of extra info. From there, we talked about the following. Where does fusion occur? Fusion naturally occurs in the stars, and that's where hydrogen is fused into helium, guys, and obviously energy is released. And look, I've done the equation there. Hydrogen 111 plus hydrogen 111 goes to make helium 4-2He, plus energy is released. And that's where all the life on Earth is from, the sun. And why should we explore fusion? Was obviously we've got plenty of fuel on Earth, we can solve the energy crisis. And there's actually more energy released in fusion than fission per kilogram. Next of all, it's going to be, why is it difficult to build fusion reactors? Why is it difficult? It's because you're trying to bring the nuclei of two atoms together. They're both positively charged, they'll be repelled. So the key thing is going to be this, you need a very high temperature and a very high pressure for that to occur, guys. That's the last thing, guys. Okay guys, that's it for another session of CeerazzleDazzle Physics. Make sure you hit the like and subscribe button to get my channel going. Good luck in all your exams. Goodbye.